Well, good morning. I see we have 19 participants here. I'm Roger, and I'm pleased to have a chance to spend a couple hours with you this morning. Let's do the following. With 19 participants, it's nice if everyone stays muted, just in case of background noise and all. I guess everybody's been at enough Zoom meetings over the last couple of years that this is nothing new. The only thing I'd like to encourage is that for all of the interaction that you have, that is the people taking the course have with me, the instructor, let's do that by way of the Q&A box. And let's save the chat box for interaction with the hosts if there's any technical difficulty or anything like that. But if you have a comment or question on anything we cover in the course, the whole point of a live course is to have live interaction. So don't hesitate. I've always said the only bad question is the one you don't ask. And if you ask a question and the answer is coming on down the line, I'll let you know that. So. And I see a Q&A up right now, so let's see what it says. Well, let's see now. Oh, from chilly New York, yeah. Well, you know, it got down below 70 down here in Florida last night as well. So I can relate to that chilly stuff. So normally I will answer questions live, okay? Because that way everybody gets the answer relatively quickly. But if you type in the chat, then I see the little light flashes on me and I can see what the question is and respond pretty much immediately. Okay, so let's get started. There's a bit to talk about today. We're talking about the path to sustainability, and in other words, what's going on the electrical side. And well, some people may not realize it, but times are changing. It's hard for me and as a 78-year-old guy to realize that, but no, well, I think I may have ridden in one of these at a park somewhere once, but and no, I never did get a ride in one of these. First car I was in actually had a top on it. Did get a ride in one of these though. This is a plug-in hybrid, 2018 version. A little bit different, change over the previous. I can remember these typewriters. I can remember these slide rules, and I can even remember these light bulbs. So, but things are changing. We're going to talk about change today. Particularly how we generate electricity. We're still doing it this way. Maybe not the best way, but we're still doing it. And but now we're also moving into a few other ways. This looks pretty clean here. Pile of dirt there, but there's grass is going to grow on that. This is a relatively new wind farm. And a relatively new solar farm here. And of course, we've got acres and acres and acres and acres of rooftops that will also accommodate solar energy. And a lot of that is happening as we're speaking right now. That's my particular, my background is electrical engineering. Right now, I am working in the solar industry. I am checking plans for solar systems for a former student of mine, actually. And in the last 14 or 15 months, we've gone over 20 megawatts of residential solar that we've designed for permitting. So that wasn't happening that way 10 years ago, no way. So times are changing. I see there are notes in the chat box, but for comments, I'm going to be looking in the Q&A box. I'm going to look at the chat box just now. Oh, a question about, oh, okay. Yeah, okay, it is in fact between the hosts, so that's good. Here's a Q&A though, let's see what that is. No, we did that already. Okay. And back, whoops, I'm going to keep clicking. Okay. So what's going on with electrical generation? Well, for one thing, it's moving from inefficient to efficient. It's moving from fossil to renewable. It's moving from dirty to clean. It's moving from predictable to less predictable. Of course, there's the downside. Nothing is perfect. Even the sun is going to burn out in another 4.5 billion years. So we're going to have 8 minutes to start looking for another source after that. One of the challenges is the less predictable nature of the wind and the sun. Of course, we're pretty well sure that the sun is go down at night and come up in the morning. It has been doing that for a long, long time. But whether it'll be cloudy during the day, that's another issue, and that cuts back on the solar power. And the wind blows at night, and down here it's been blowing quite a bit recently. But, and I gather folks up in New York and New England are having a good time with some cool weather as well. Get that from your friends who come down here to visit. There's been some storage. There's been pumped hydro. It's been around for at least 50 or 60 years. They discovered back when nuclear first started coming online that it was a real problem to try to slow it down at night and bring it up again in the morning. They'd like to keep it running at a constant rate. And so when they didn't need it to run various daytime activities, they decided they'd pump water uphill and then let that water come back downhill the next morning to make some electricity. So that's been around for a long time, but of course now we've got lithium batteries and a lot of other interesting things. We'll touch on that a little bit as well. And around the world, more high voltage DC transmission lines are coming in. And there's a whole lot more control and data analysis in order to maximize the performance of the various electrical generation systems. So in photovoltaics, they've been getting cheaper. And just as a clue about what might be on the quiz, quiz questions tend to focus on some things like this, like, for example, notice that in 1975, you would pay more than $100 a watt for solar electricity generation cells, modules, actually. The encapsulated cells are in the modules. And today, 2020 and 2022 as well, the cost is in the neighborhood of 30 cents a watt. So we're seeing a reduction in price of a factor of 300 since 1975 in the cost of photovoltaics. And this reduction by a factor of 300 is based on not $1975 either. It's just based on the dollar of the day. So if you take into account inflation, the deflation rate of the cost of solar has been going down a whole lot more than even it looks on this graph where we're just looking at $1975 all the way through. Well, actually, that's not true. In 1975, we're looking at $1975. In 2020, we're looking at $2020. Okay, so let's take a look at worldwide solar photovoltaic shipments. This graph was originally drawn in 2014 up to 2014. And a few projections were made by the author here, and the green one was the optimistic and the blue was the pessimistic as to what might happen over the next decade or so. And the actual black one is what's really happening. And up through 2019, it was staying right in between those two guidelines, and it is still following on track. So that means that if you take a look at that vertical axis, that is a logarithmic axis. And as every good engineer knows, when you see a linear presentation on a semi-log curve, you are talking about exponential growth. So in terms of cost, you could install residential photovoltaic system for about $3 a watt. 2019 utility installs were about $1.50 a watt. So utility generated solar electricity is less expensive than the stuff you generate on your roof. On the other hand, the utility generated electricity has to find its way to transmission lines and distribution lines. And so there's a whole lot more effort in getting it to you than if it's up on top of your roof with some battery backup, so that if there's a power outage from an ice storm, we have them all the time down here in Florida, and I know you have hurricanes up in New York. So if you have these power outages, it's nice to have a little battery backup with that solar on your roof, so you can still continue keeping your refrigerators cold. And we used to say here that the people with solar on their roof had hot water and cold beer while their neighbors didn't when there was a hurricane. So let's look at some numbers. In 2018, 2.4 gigawatts of residential PV in the United States were installed just in that 1 year alone. In 2018, 11.7 gigawatts of total solar was installed in the United States. So that means we're adding the utility and the commercial and industrial. So residential is 20% of the total amount of solar photovoltaics that's being generated in the United States currently. Globally in 2018, worldwide 104 gigawatts were added. So we're not the only game in town here with our 11.7. In fact, we're somewhere down the neighborhood of 11% of the worldwide total. China is the leader, 47 gigawatts in 2018. And India, right on up there with us, have 11 gigawatts in 2018. In the United States in 2018, there were 242,000 solar industry jobs. PV efficiencies continue to improve and the reliability continues to improve and the costs continue to decline. They're kind of leveling a bit now because some of the, for example, racking, if it's being shipped, because of the shipping delays and the supply line disruption, there are some glitches on the curves here. But presumably, because of the technological advances, the costs will still overall continue to decline. But even still, well, let's look at the wind first. What's happening there? Well, 101,738 jobs in 2016 in the United States, according to the United States Department of Energy. 54 gigawatts of wind power worldwide installed in 2016. Now that's not the total that was there, but in 2016 alone, 54 gigawatts were installed and added to the total, because the cumulative total in 2016 was 4,866 gigawatts. So wind got off to a slightly earlier start than solar in terms of its major increase in the contribution to the grid power. Then there were 945,000 small wind turbines worldwide as well. And that back in 2014, their capacity was 830 megawatts. And it's interesting to go to places like Yellowknife, Northwest Territories in Canada and observe the wind turbines up there, because during the long winter's night, the wind still blows. So they depend a lot on them to make electricity in the winter when it's kind of dark outside. Just as a comparison, a large wind turbine can generate around 2,300 kilowatt hours per year for each kilowatt installed. And that's about comparable to installing photovoltaics in the desert. So this is a magic number for the desert, 2,300 kilowatt hours per kilowatt per year. And cost of wind turbines about $1.50 to $2 a watt. Back in the 2018 to 2020 range, it's probably going down a bit. Although once again, because of supply chain disruptions, I don't have the direct numbers. But at that kind of a construction cost and with zero fuel costs, that means a wind turbine located in the right place can pay for itself with pretty quickly and generate electricity at a relatively low dollars per kilowatt or cents per kilowatt hour that one needs to pay in order to pay for the installation of the turbine itself. Thing about wind is that it requires sustained winds because we've talked about rotating machines here, and when you have gusty winds, that's really tough on the bearings, and it creates a little more of a maintenance problem. So that's generally why they're so high, because the nice tall windmill, the winds are a little bit more sustainable at a higher altitude. I guess I think of the big windmill in almost downtown Boston, that big turbine. It just stands right out when you're driving along. So they're around, and we don't have any in Florida because we don't have enough sustained winds. So we have very few to speak of, but other places where it's more windy, the Buffalo Ridge, Minnesota, Western Texas, California, along Highway 2 up in Massachusetts and so forth, lots of areas. And believe me, the people who install wind power know where the wind is. Worldwide growth in wind power has been more linear over the years between 2006 and 2018, but you notice that the capacity is approaching 7,000 gigawatts. Where is it? Well, once again, China is ahead in wind, ahead in PV. United States number 2, Germany number 3, and Turkey, believe it or not, is doing fairly well in wind power considering the size of the country. This isn't total capacity here in megawatts, not in megawatt hours generated. So you then have to convert, you have to go by the site and figure out for that particular site, how many megawatt hours a year can you expect for each megawatt that you install. And like I just mentioned, wind power is not necessarily cost effective everywhere. But in general, photovoltaics is. And in fact, we are noticing now here in Florida and in other areas where photovoltaics not only are cost effective when they're pointing directly south, but they can be installed on east roofs, west roofs, and even on north roofs and still generate cost-effective electricity compared to utility costs. So in terms of where it can be located, photovoltaics have a little advantage over wind in that regard. The other advantage photovoltaics has is the production is directly proportional to the sunlight intensity, as opposed to proportional to the square of, not even proportional, but the forces. Wind forces are proportional to the square of the wind velocity. But you also know that power is equal to force times velocity. So there we're getting into the cube. So if your wind power drops, if your wind velocity drops by a factor of 2, your power output drops by a factor of 8. And that's kind of inconvenient, which is why you want your sustained winds. So what's been happening with the rest of the sources? Well, for a long time, the fossils were fairly evenly, all three were, the oil, the coal, and the natural gas were in the neighborhood of 100 quads per year. And that's the energy produced, but usually the energy produced is the energy used. They jumped up a bit between 2014 and 2019, as you can see. And the question is, where are we going as far as fossil fuel production? But the encouraging one on this picture here is the green one, because that's the renewables other than hydro. The blue one is hydro. So hydro is increasing, not as fast, again, because hydro is very site dependent. And when you run out of hills, you kind of run out of hydro. But, or if you run out of rain or water, which in some cases that's happening. But with the sun still reliably rising every morning, we still have a source, and there's plenty of rooftops and plenty of areas still for installing solar. So that exponential growth has continued through 2019 and it appears that it's going to continue going on. So the question is, how long does this have to happen before the solar replaces the fossils? And if you project these out, and listen carefully to this, it looks like the green and the black are going to converge somewhere around 2035. Now, if in fact the green is replacing the black, the fossil, that would mean the black curve is going to start pointing downward, which you notice is the case for the nuclear curve, which is the one with the upside down, or call them the deltas. You can see the nuclear curve there is pretty close to the hydro curve over the years, and then the hydro starts going up, the nuclear starts going down. And the reason is very simple. The cost of new nuclear is a whole lot more expensive than the cost of other new sources. So it's an economics issue as opposed to anything else that one might want to assign to it. It's strictly economics. You notice nuclear went up a little bit in 2019 over 2014. That's because they've been fixing the old plants, but not because they're building new ones. This is energy production here. So we're talking kilowatt hours now, not capacity. And it's interesting to notice that in 2019, the renewables worldwide exceeded nuclear worldwide production. So this is not just a toy anymore. This is for real. Now, here's this is the way people like to compare energy sources, and it's called the levelized cost of energy in cents per kilowatt hour. And what this means is we add up all the costs of the energy source: the cost to build it, the cost to operate it, to maintain it, the fuel costs, the decommissioning costs, and adding those all up and doing time value of money, if you want to, you come up with a number that you need to charge for your electricity in order to get your initial investment back. And that's your levelized cost of energy. And let's look at that for a few things. Natural gas, 5.6 cents, not too bad. Advanced nuclear, 11.8. Onshore wind, 4.1. Aha, less than natural gas. Photovoltaics, 4.0. Now this 4.0 is kind of an average over all sources. Residential being higher, utility being lower, but if we average them all with the 80-20, whatever, photovoltaics, you're looking at around 4 cents. Hydro, 6.4 cents. Now, this is information from a publication by Lazard, and part of this is based on assumptions of the actual duty cycle of the source. For example, if you've got natural gas and you run it 24/7, that's the 100% duty cycle. But if you have a peaking power plant where you only turn it on for 3 hours a day, then that's off for 21 hours a day when it could be making electricity and helping to pay for itself. So it's only helping to pay for itself 3 hours a day. As a result, you need to charge more for that electricity, which is why the peaking electricity is more expensive than the baseload electricity, which is being generated pretty much constantly all day long. The one with the star, the asterisk on hydro, goes back to the Department of Energy estimate for 2017 on 6.4 cents. Now, there are going to be some major changes in the grid use, and that will impact engineering and contracting, and these are things we kind of want to be aware of. I see some Q's and A's, so let's take a look up there and see what we got. LCOE for offshore wind, higher or lower than 4.1? Let's see, did I just, oh, okay, here, I learned recently that even gas furnaces are unpredictable. Ours became carbonized a few weeks ago and we had to install a different heat source. Yeah, I wonder if you considered installing a heat pump. There's a very, you might comment on that. What did you install? Because I'm reading now about heat pumps that have extremely high coefficients of performance and are operable down to about minus 13 Fahrenheit. Whereas 20, 30 years ago, yeah, okay. And you might answer on that one also, whether you're happy with that heat pump and whether what effect that might, maybe you've had a chance to observe what that has done to your electric bills or to your overall fuel bills, because after all, you're not paying for, if you're using gas, you're paying for gas. How does your electric bill compare with your gas bill with that new heat pump? Because it appears to me that heat pumps are the way to go now. They seem to be much more efficient energy-wise, carbon-wise, everything else than fossil sources for heating. Let's see, the LCOE for offshore wind, higher or lower than 4.1. Offshore wind is more expensive than onshore wind because it's a little more complicated to build them, a little more complicated to get the power onshore. But as I recall, it's about 2 cents a kilowatt hour higher than onshore wind. Still cost effective. Look at it this way, utilities will not be building and investors will not be building large offshore wind farms unless they could sell that electricity. And the only way you can sell the electricity is for it to be competitive. So let's see, Long Island wind farm in Rhode Island. Yeah, I'm not sure how the numbers look there, but I can assure you that they would not have built that thing unless they were confident there was enough wind to make enough electricity and that wind farm would last long enough to pay for itself. Investors are pretty fussy about that. So, okay, great. Good questions, folks. I appreciate that. And I'm going to check some of these off so we don't repeat ourselves. Okay, so there we go with the Q's and A's. X that out, and let's talk about major changes in grid use. Electric vehicles are going to make big difference. We'll talk about them a bit. In fact, maybe a lot, because I see that as a major thing we engineers and architects need to start dealing with. And that includes plug-in hybrids as well as all electrics. During the pandemic, with our plug-in hybrid, we did not go to the gas station for 18 months in a row. We were able to run all the electric for 18 months. So depending on how you drive them, a plug-in hybrid is every bit as good as an all-electric. Plus, it has a gasoline backup, which of course you'd rather not have to have. And believe me, you hop in a Tesla and start driving around, you never want to ride in another hot Mustang again. Energy efficiency, major inroads in lighting, refrigeration, almost everything. And that's where the heat pumps come in as well. Zero energy buildings. It is now cost effective to build buildings, not that they don't use any energy, but they have zero net energy. They produce as much energy as they buy from the grid or from external sources. And that's the definition of a zero energy building. And it is now possible to build zero energy buildings that are more cost effective than buildings that have energy bills, because the cost of improving the building to be a net zero energy building, the additional mortgage cost is less than the savings that you have in your energy bills. And that is pretty much nationwide. A number of studies have been done to show that. So you can count on building codes to be getting tighter and tighter and tighter as the years go by. And I wouldn't be surprised in 5 years from now, the building codes are going to be all encouraging zero energy buildings. So let's have a look in the Q's and A's here. Large scale solar versus agricultural use of the same land. That's something that disturbs me a little bit. And Julius, every time I think about that, and every time I get on the freeway, I think, if we ask that same question when we talk about freeways versus trains. Now, the other part of the large scale solar versus agricultural is that people are paying attention to that, and they are figuring out ways of multi-use for large scale solar. And I mean, I personally am a major fan of rooftop solar because the rooftops are there and they are happy to have solar. The solar makes the roof last longer. It holds it down better. You put in a 4-inch slab by 5/16 lag screw to hold down your roof. It's a whole lot better than a nail. So yeah, there are trade-offs with large-scale solar, no question about it. And there has to be some sort of mitigation so that we come out ahead in terms of the carbon and in terms of the food and everything else. So it's a good answer. It's a good concern. I appreciate your pointing that out. And let's see, there's something in the chat box, but I am going to assume that chat box questions are administrative, and our host will handle those, and I'm going to be watching the Q's and A's. Okay, zero energy buildings. So these are some things we want to talk about: distributed generation and energy storage. Energy storage is going to be big time. And during this decade, it's projected that energy storage is going to just grow like crazy. Let's talk a while about electric vehicles. We've been talking generalities. Now let's get into some specifics here. A lot of choices out there. The one on top right is my favorite, of course. But then again, I don't have 150,000 to shell out for that creature, so I'm going to have to let that one go by the wayside for the moment. The couple on the bottom, though, they're fairly reasonable choices, and that Toyota up there is not a bad choice either. So there's two types. There's the all-electric. They generally have a range between 100 and 400 miles. They have battery storage between about 30 kilowatt hours and 100 kilowatt hours. Most of the batteries are lithium-based, and the charging times depend on the level of charging, and we're going to talk about that. There's a whole new way of life with electric vehicle. Rather than going for gas every week or two, you just fill it up with electricity in your garage after you get home at night, overnight, and never bother to go someplace to get electricity, unless you live in a condominium where they won't let you plug in your electric vehicle. And I've got neighbors where they think that's a bad thing, and clearly they have only been doing guessing on that, because if the engineers came in, they would discover that the electric service that was put in that building 40 years ago was based on a very conservative estimate of the amount of electricity that would be used: incandescent lights, inefficient air conditioning, inefficient this, inefficient that, and we have moved toward efficiency. And I can tell you that pretty much every building around has got leftover electricity now on their electric service because of it being conservatively designed. So then we're going to talk about that in a minute. So let's move along here. We talked about plug-in hybrids, and of course they have a larger battery pack than you put in a regular hybrid, and they can be charged by plugging into an electrical outlet. The battery pack in a typical plug-in hybrid is in the neighborhood of 15 to 20 kilowatt hours, and that gives you a range on electric only up around 50 miles. So if you drive less than 50 miles a day, and if you can charge at 5 miles an hour, then 10 hours overnight charges you up for the next day. Range of a plug-in hybrid, though, is up to about 400 miles because you've got about 8 gallons of gas in the tank to pick up if the electricity goes away. And you can do the math there: 8 gallons for 350 miles. 350 divided by 8. Let's see, I have to have a calculator to do that. 350 divided by 8. That's 43.75 miles per gallon when they're run on gas only. And again, this is these numbers vary depending how you drive the thing. But anyway, lithium-based batteries and variable charging times. So let's talk about charging for a little while, because maybe not for engineers, but for most people, electric vehicle charging is a bit of a mystery. It's all down in NEC, National Electrical Code 625.2. If you're an electrical engineer, if you're not an electrical engineer, you all know that just like ASCE 716 is the guideline for civil engineer design, National Electrical Code, the NFPA 70 is the rule book for the electrical engineers. And of course, the ASHRAE 90, I'm not sure that's the heating, refrigeration, air conditioning rule book and so forth. So we all have our manuals that we use to. So in any case, NEC 625.2 defines an automotive type vehicle for on-road use as that's what an electric vehicle is, and that could be passenger automobiles, buses, trucks, vans, neighborhood electric vehicles, electric motorcycles, electric golf carts, and forklifts are not included because they are not intended for use on the road. And the other thing is electric vehicles have to use rechargeable batteries, so these won't work. They don't even put those in hearing aids anymore. They make hearing aids rechargeable. Anyway, let's do some fuel cost comparisons. This is kind of fun. When I did this slide, things were a little different from what they are now, but everybody here is an engineer or architect. You took a few math courses, so it shouldn't be a big issue. This is a lousy assumption of gasoline at 275 or $2.75 a gallon, of course. And even electricity at 15 cents a kilowatt hour, that's a whole lot better assumption in most places. We're still paying around 13 down here. If you're on a general service demand rate, you're paying about 8 cents a kilowatt hour for your kilowatt hours. And but gasoline is more like $4.75 a gallon now. And I'm guessing it's probably about the same up north. Not everywhere, maybe as little as $4 a gallon some places, who knows. But let's look at this full-size SUV at 20 miles per gallon, and we can just do the math easily. 1,000 miles at it was going to use 50 gallons of gas. That's $137.50. If we use that 50 gallons at $4, obviously 50 times $4, that's $200 for the gas instead of $137.50. So, you know, you can, as long as you have the slides, you can redo the math with the going rates on these things and make the comparisons yourself next year. You got a small SUV, that might get 33.3 miles per gallon. It only costs you around $100. Again, depending on whether you're using the $5 gas or the $2.75 gas. Or you might have a hybrid, like this Honda hybrid, and 1,000 miles at 55 miles per gallon is only 18.2 gallons or $50. Or you could have an electric vehicle or a plug-in hybrid using only electric, and good number for average mileage, unless you drive like a maniac, is 4 miles per kilowatt hour. So that means you use 250 kilowatt hours, and that's going to cost you $37.50 if you're buying 15-cent electricity. So the electrics are cheaper to drive, and they're also cheaper to maintain because there aren't as many carburetors and all kinds of stuff like that can play games with you. They've got the electric engine and the batteries and the controllers and so forth. But in general, the maintenance is less. And if you use this plug-in hybrid half and half on electricity and half on gas, it's going to cost you $46.25 for that 1,000 miles. So still a pretty good deal. So the economics of electric cars and plug-in hybrids are pretty good these days in terms of their fuel cost. The actual cost for the car you kind of pay for a car what you want to pay for a car, whether you're going to pay 20,000 or 100,000 or more. Most people don't consider the life cycle cost of the car and what they spend on a car. People buy cars for the comfort of the car. Some buy them for the performance of the car, and performance can be measured a number of ways, of course, one of which is the fuel efficiency. Charging levels. Let's hit the Q&A. Let's catch it right away. Any idea how cost of electricity at level 3 commercial charging facility compares? You know what? I am not sure, because level 3 commercial charging, that we're going to come to that in a minute. The level 1, level 2, level 3 charging. And Mark, I've never priced that out, so I don't have an answer. But if anyone else has an answer to Mark's question, please let us know. Okay, I have not, I've never stopped at a commercial charging facility, and I do have some friends who own Teslas. I just never bothered to ask them where they go to get their Teslas charged, if they go for the, I know sometimes the Tesla level 3s, I think the price of the car includes being able to go to a Tesla place and getting a free fill. I don't know. Let's encourage others to chime in on that. And what does it cost per kilowatt hour to charge your Tesla or any other? Normally, the Tesla is the one you're going to do the fast charge on, the level 3 charge. Most of the other cars, level 2 is perfectly good because they get enough range you can charge them at night. The level 3 would mostly only be used if you're traveling a long distance. So let's see, but otherwise, Mark, thank you for that question, because you just proved that I don't know it all. And every day there's more new stuff that comes up that we all have to learn. So let's talk about the charging levels, since you mentioned level 3. Level 1 is your standard 120 volt outlet. And the charging power is somewhere in the neighborhood of between 1,200 and 1,440 watts. Okay, so that means that 1,200 watts, that's 1.2 kilowatt hours per hour. And so when you know how many miles you get per kilowatt hour, then you have a pretty good idea how many miles you get per hour of charging, or in other words, miles per hour, which is a new use of miles per hour, is in terms of charging. So level 2 will plug into either 208 or 240, single phase, by the way, and generally charge somewhere in the 3,000 to 7,000 watt range. It is increasing, somewhere in the higher than 7,000 now. But just in terms of circuit sizes, you can do 3,000 watts at 208 with a 2-pole 20 amp circuit breaker. You can do 7,000 watts at 208 volts with a 40 amp circuit breaker. You can do 3,000 at 240. You can do that with the 20 amp circuit breaker. And you can do 7,000 at 240 with a 40 amp circuit breaker. So you're looking at somewhere in the neighborhood of 40, 50 amps, maybe even 60 for the newer level 2 charges that charge a little faster. But level 2 is as high as you're going to go in a residential. And the reason is because level 3 is somewhere in the 125,000 watt range, or 125 kilowatts. And that's your fast charge. Now, given that the 125,000 watts will give you 125 kilowatt hours per hour, and the big Tesla only holds 100 kilowatt hours, it means less than an hour to charge it. But the faster you charge, remember, that's higher current going in, and that means you're heating up those batteries. It means those batteries have to be able to manage that heat, and they do, otherwise they wouldn't make these chargers. But this is an interesting thing, because when you're dumping 100 kilowatt hours into a battery pack in a half an hour, actually they don't do that. They normally only give you 80. So, but anyway, in a half hour, you can get pretty much half a tank full of electricity. I'm sorry, 80% of a tank of electricity with the level 3 charger. But even if they run at 460 volts, three phase, it's a 157 amp circuit. So as a residential option, it's got to be a whopping big residence. And furthermore, the utility has to be willing to serve that residence with three-phase service. And you don't see very many of those out there. So those are your three levels of charging. And generally, most electric vehicle users can get by with level 1. I wasn't sure about that when we first got our car in 2018, but we've been charging level 1 overnight for the whole life of the car. And we went for 18 months during the pandemic without having to add gas. Made a few trips to Orlando, 400 miles round trip, had to use some gas on those trips. Here's some Q's and A's. Let's take a look what we got. Okay, regarding solar, I don't think most contractors in our area would be willing to sell a battery system to enable us to use the system when the power grid is down. Don't know if the utility company would allow it. Is it allowed in most states? The answer is, as far as I know, it is. Utilities in Florida are not happy with residential solar. They're trying to get rid of net metering right now. But battery backup is good for the utility, especially with IEEE 1547-2000 out there, because that allows your battery to talk to the utility. And if the utility needs electricity, it can negotiate with your battery system for a price. And if it can buy it cheaper from your batteries than it can from another peaking source, it'll buy it from your batteries in your house. From the standpoint of our own business, we have installed typical installations around 10 kilowatt hours of backup, 10 or 20, but we've installed up to 40, and in one case, I think we did 80. So in Florida, battery backup is kind of popular. Just mostly people are buying it just as hurricane. They've discovered that gasoline and fossil generators really don't smell very good, and they're very loud and noisy, whereas solar is quiet and dependable and very, very helpful in emergency times. So I think you're right, though. The batteries are in New York, because I have some relatives up there, and they were considering putting in batteries, and they decided the cost was way too high. So it seems like the name of the game in New York is to use fossil fuel backup with solar. And I know for a fact that a lot of solar is getting installed in New York and New England. Battery backup, they can't really tell you you can't do it. If you use it all internally and none of it goes back to the grid, then nobody can stop you from battery backup. I mean, I suppose a local authority having jurisdiction could, but since it's covered very in detail in the National Electrical Code, all the safety features, it would be very difficult for an authority having jurisdiction to say, sorry guys, no battery backup, not safe, because that is absolutely not true. And I mean, in that case, you'd have to argue that gasoline is not safe either. It might burn. My experience with public charging stations, most of them are level 2. That's from Carol. I've parked out a few of them. We have a few at our local university, libraries, and so forth. And level 2 is very comfortable for age. In fact, what you see off to the right is a level 2 charging station at an automobile dealership. And since they're using about 10 kW, and if they've got a lot of them, 10, 15, 20, you use the same load calculation where you do the first 10,000 watts at, if it's residential, first 10,000 at 100% and the remainder at 40%. So you get some diversification on these. So let's see, does the utility extract stored energy in the Powerwall system or also in the EV itself? Well, it's possible for it to do it with both of them. The Powerwall generally comes already equipped with the IEEE 1547 2000 interface. Most of the EVs don't have it yet, but and what's missing is the way, a means of turning the DC from the automobile back into AC to sell back. So one inverter is missing in that system in order to sell back to the utility. Because you're charging, you're bringing in AC and it's converted to DC in the car. So to turn the car into an equivalent power wall, you have to be able to get AC back out of it again. So add in one inverter and you're back in business again. Let's see, Walter, Carol, Anonymous. Okay, I think we got the answers there. So I'm going to say that we answered that live and that we're done with those. Click, 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 click. So let's take a look at moving on beyond charging levels. Other than observing that the claim is that higher charging level rates are on the horizon, I understand the level 2 chargers now they're using with the Teslas are more like 9,000 watts. Maybe somebody can correct me on that. But 9,000 watts is still, well, let's see, what's the circuit? I have to figure that out. 9,000 divided by 240 is 37.5 times 1.25. Yeah, so you could do 9,000 watts with a 50 amp circuit. If you're going 10,000, you'd have to have a 60 amp circuit. So I think level 2s are moving up towards 9,000. Okay, let's see. How long does it take? Well, I've hinted at a few. But again, it's easy to do the math, so you can figure all this stuff out for yourself. If you get 1.2 kilowatt hours per hour out of a level 1 charger, and if you get 4 miles per kilowatt hour, that gives you about 4.8 miles, or roughly 5 miles per kilowatt hour. Okay, it's somewhere 4 to 5 miles per kilowatt hour, and that is roughly 5 miles per hour of charging. So if you charge at level 1, you get about 5 hours for every hour you charge. So overnight, 10 hours, 50 miles. And if you drive 20 miles back and forth to work, then you got it made, because you only have to do 4 hours of charging at night and you're all charged up with your cute little 1200 watt level 1 charger that comes in the trunk of the car when you buy the thing. No extra charge. As long as you've got a 15 or 20 amp outlet available that's not using any other large load. And typically a garage has got an extra outlet there that you can plug something into, whether it's your table saw or whatever. So now you plug your electric vehicle in and you're done now, because nothing else is connected to that circuit. Level 2 charger, 5 kilowatts rate, well, so it's proportional. So you get about 4 times as much. So therefore, you get about 20 miles per hour of charging. And this is why I say that the level 2 charger is the public chargers, because I've parked and plugged in at an airport cell phone lot for half an hour, and it increased my range by about 20 miles. So that was a pretty good confirmation that the charger up at the cell phone charging lot was a level 2. Level 3, here we already talked about that. It's more than any of the automobile battery packs. Of course, you got school bus, you got truck, and you know they're out there. Level 3 chargers are going to be important, but that's a pretty major service. You're looking at pretty much a 600 amp service, 3-phase. If you want to get into the level 3 charging business, and plenty of people are doing it. Don't get me wrong, but I don't think, for example, a cute little BMW i3 can be charged at that rate, because I don't think the batteries are capable of taking that big of a rate of charge without overheating. I think they have current limiting it within the vehicle that would slow down that level 3 charger, even if you tried to charge it at level 3. I think it's also true that level 3 charging is a DC charge rather than an AC charge, and that somebody might correct me on that as well. Feel free. If I say something that I think, what I think is not always the right thing, but I believe I heard one time that you charge through a different port when you do the level 3. And I think that's because it's a DC charge, goes straight to the batteries rather than through an inverter. Okay, so what else we got here? What do we want in a charger? Well, there's basic charger, and you want to be compatible with any car you plug into it. You want to be able to communicate. For example, the car charger, when you're plugged in, you can dial up on your cell phone and determine your state of charge of your battery, whether you're full, empty, or how many miles you got, or whatever the measurement is. And also, you'd like it to charge your car in the amount of time that you have available for charging the car at the lowest possible installation cost. And of course, it has to be safe. And there's all kinds of rules that are in effect now. That there's a lot of standardization in the chargers. They mostly all use the same connector, for example, which is this one right here. Now, if you look at those 5, 3 of those are the high power, and then those 2 little baby ones are the communication link. And they're the ones that light up a light in your car if you try to drive away without unplugging from the charging station. They tell you that the car is plugged in or something like that, and they will not let you drive away until you unplug. And those are the ones that send the information to your cell phone and so forth on the amount of charge. They talk to the control system within the car. So I could have showed the arrow in the explanation. There are advanced chargers, and it would be nice if they were bidirectional. We've talked about that because that way I see this as a major contributor to energy storage within the next 10 years, is taking advantage of IEEE 1547-2000, which basically says that your car could be parked in a charging station at work, be fully charged by noon, and ready for you to drive home, and you don't need all that electricity to drive home. And the utility can then dial up your car at its own IP address, Internet of Things, and say, hey, I see that you're plugged in, and I wonder if you can sell me a little electricity. I could sure use an extra 5 kW right now. And if you could do that for an hour, I'd be happy to pay you 25 cents for the kilowatt hour for that. And your car in within 100 milliseconds, you got a transaction. And so you leave work with 5 kilowatt hours less in your electric tank, which you refill again when you go home at night on nighttime electricity rates. So I see that. I can't see how we would not be doing that with the next 5 years. So keep your eyes and ears open, folks, and see if this crazy guy who's talking to you today is right or wrong on this deal. They need to be adaptable. They need to be portable. That's desirable if you want to take it with you on trip. So what are some typical charger? Well, this is the one that came with our car. You plug it into the wall. It's got that transformer-like thing. It has all the communication stuff in it, and also an isolator, so that you are connecting it into the vehicle. And that's the J1772 connector that folks have pretty well standardized on. This one is the one you saw a little earlier. That's the level 2 charger, very convenient outdoors, and set up so that they can charge you for the electricity of the credit card or one way or another. There are some interesting complexities here in terms of third-party vendors. In Florida, we have this crazy rule that says that you cannot buy electricity from the utility and sell it back to somebody. So something's got to change in order for these to be able to sell back. unless the utility owns them, then they would be selling you electricity directly from the utility. And I'm sure the utilities would prefer to have that, but we're going to see that's going to be an interesting thing to sort out over the next few years. This is a wall-mounted level 2 that you might put in your garage. Here's the level 2 that happens to be out at this. You notice it's got two different chargers, one for the car on the right, one on the left. And this is out at the local university. I've used that one. It's always kind of nice to let the university buy you a little bit of electricity. And oh, wait a minute. No, I'm sorry. This one is at the local library. The one, the 1, 2, 3, 4th from the left is at the local library. And so the town belongs, the library belongs to the city. So the city buys your electricity. And the other one, the ground mount level 2, is at the local university. You can see that looks a lot more like a university campus with that building in the background and so forth. So they come in all shapes and sizes. I'm just going to quickly go through here. Let's see how we're doing on time. 11:03, we're okay. Applicable codes and standards for those of you who are interested in doing more on EV charging. NEC 625, NEMA has a lot of stuff on twist lock connectors, standardization of the connectors. This is a J1772 from the Society of Automotive Engineers. They want to make sure it looks like you're putting gas into your car instead of electricity, so they make the thing look just like a gas pump. And then there's the open charge point protocol, which this enables communicating among different chargers, such that if you wanted to do a diversified load, have one plug, one connection to the utility with multiple chargers, the chargers can talk to each other and limit the total amount that's purchased from the utility at any one time, and in effect share the charging amongst a number of vehicles without having to have the demand at some unreasonably high rate. It's more of a demand limiting device, and also something that might be more affordable for a place like a condominium, which generally does bring in 3-phase for a larger one, or a business or whatever. The UL 2202 is the standard for EV charging systems. And if you want a copy of that, it's a mere $1,000. So I didn't buy one last year. I may not buy one next year. I'll try to find a friend who has one. UL 2231 talks about personal protective systems for EV supply circuits. Well, okay. It turns out that of course, you got the supply circuits inside the car as well, but outside the car, you can pretty well be assured that the National Electrical Code follows all the requirements of UL 2231. And here's a reference if you want to dig it out. Just go to this reference here and read it over in gory detail. And here's another one about the open charge point protocol. So what if you want to add a charger? Let's just have a look and see what it involves. Again, we're talking seem to be spending a lot of time on electric vehicles, but I think electric vehicle charging and use is going to be proportionately more and more important in terms of the future electric service and the future electric grid. And that's why I am adding things, because I think engineers ought to know about this stuff. It's stuff you're going to come in contact with. I'm more likely than you'll come in contact with a 100 megawatt battery storage system, for example. But almost everybody's going to get, your friends, your neighbors going to ask you, what about these electric vehicles? And you're an engineer, you're supposed to have all the answers. So, yeah, what are you going to do? Might as well learn about this stuff. NEC 220.83 gives you the rules for an existing single-family dwelling, and 220.84 gives you the rules for an existing multifamily if you want to add the charger, okay? It's right there. And for other sites, other sections apply if you have a business, whatever. So let's do an example on 220.83, okay? Let's do a load calculation for a 1,500 square foot dwelling, okay? No new air conditioning or heat. We're just going to add a new charger. What's it going to do to your diversified load, okay? Well, here we go. Basic rule, general lighting, 3 volt amperes per square foot. The volt ampere is just volts times amps, which if it's DC, it's a watt. If it's AC, it could be a watt, or it could be, if the current and the system has a so-called power factor less than 1, then volt ampere is what you get by multiplying volts times amps. But the power in a circuit is always less than or equal to the volt amperes in a circuit. Okay, the volt amperes can't exceed the power. And what's left over there is the so-called reactive power. And interestingly, they do not add linearly. They add using x squared plus y squared equals z squared kind of formula. Typical dwelling unit though has a washer, dryer, refrigerator, and 5 appliance circuits, and they're going to add up to 16,000 volt amps. They also have electric heater, electric range, and you treat this 5.5 kW level 2 charger the same as you do an electric range or an electric water heater or any other additional electric, like a swimming pool pump, for example. Just add it right in, and the sum total of the volt amps of all those things, including the new one, is 22,000. And then the formula is very simple. You've got 22,000, and so you got 3,600 plus 16,000 plus 22,000. You take the first 8,000 at 100%. Well, 100% of 8,000 is 8,000. And what's left over after you take 8,000 away from the sum of the 3 on top, you take 40% of that, and that gives you 15,240 volt amperes as your calculated load or your diversified load. And if you divide that by 240, that's 96.8 amps. So for this 1,500 square foot dwelling, if you've got anything bigger than 100 amp service, and by the way, 100 amps is minimum allowed, you can install, more than likely, unless you got some weird stuff in addition, like swimming pool pumps and who knows what else. But you use this procedure to calculate, and effectively, you're throwing in that additional, say 5.5 kW. Let's use 7.2 kW just because I can take 7,200 and divide that by 240, and that's 30 amps. But then if we take 40% of that times 0.4, that only adds 12 amps to your service size in order to accommodate a 7,200 watt level 2 charger. So this misconception out there that, wow, this just overloads building terribly, it is so wrong. And in my condo, we have 43 units. So some of the bigger ones have 175 amp services. Most have 150 amp services. We can allow a level 2 charger for every single unit tied into their very own electric service. The building would be fine and the owners would be fine. We wouldn't have to change a thing. But still, there are folks out there who love their gasoline vehicles, who love to make the garages smelly, and they're afraid of electric vehicles. And folks, I'm telling you, here's the numbers for you. And having experienced this piece of equipment for 3.5 years myself, I can tell you that it all makes sense. And I don't sell electric cars. I'm an electrical engineer, but I certainly do believe in them as a way of the future. So in any case, 100 amps, you're good to go. 2-pole 30 amp breaker, maybe a 2-pole 40. 220.87 says, well, hey, we can just look at the maximum peak demand over the last 12 months. If you can figure out what it is. That's a long period of time, though, to put a meter on and look at maximum peak demand. Most dwelling units don't have demand meters on them. So therefore, the code also says that you can measure demand for a month under conditions consistent with maximum use. And demand is kilowatts, the maximum power that's being drawn from the utility at any one time. Okay, and so it wouldn't make sense really to measure your maximum demand almost anywhere in May, because it's not hot and it's not cold. It's the swing season. That's when they take down all nuclears for maintenance, because they don't sell as much electricity then. So it's okay to measure both line currents, use the larger one as your demand, and then from that you move on and add, you take 125% of the maximum monthly demand, and then you compare it with what you got on 220.83 and take whichever is smaller. It's perfectly okay to do that, because this takes into account that units are generally more efficient now with all the LEDs and things than they used to be. So therefore, more than likely, the calculation you get in 220.83 is going to be a whole lot more than what you're really using. And that's why 220.87 comes in handy. So if you do the 220.87 and you come less than 23.24, then you use that one instead. Where's the branch circuit tie in? Here's a question. Let's take a look, see what we got. In the example regarding residential home, how would you get 120 to 40 volts? I followed the example until a previous line. Oh, well, let's see. In a residential, the service is 120 or 240. You know, you can plug in your lights at 120 volts. You can plug in your water heater at 240. And you've got a plus 120, you've got a minus 120. And the difference between the two is 240. So in other words, you've got two different lines. Line one is 120 volts to neutral or ground. And line two is minus 120 volts to neutral or ground. And the difference between plus 120 and minus 120 is 240. Now, I'm not sure that's the answer to your question, but residentials, there's electric service to a residential home is, unless it's in a condo where you get 120, 208. If it's single family detached, for sure, you're going to have 120, 240. Unless it's some huge 10,000 square foot thing where you got special permission from the utility to get a 3-phase service. All right, so please tell me if that's not the answer you were looking for, or if I misinterpreted your question. Otherwise, that's what we're talking about when we talk about 120, 240, single phase. Okay. So where do you connect it in? Well, if you've got an open space in your, for a extra circuit breaker in your electrical panel, then you connect it in there. It's probably, I mean, if you're just using a level 1, you just needed a single pole available, a 1-pole circuit breaker. If you're doing a level 2, you're going to have room for a 2-pole circuit breaker. One half of that circuit breaker connects to line 1 and the other half connects to line 2. Okay. But a lot of main distribution panels are full and there's no more room for an electric vehicle charger. And there's no more room to connect the solar system, for example, either. So you got to do something else. So if it's not convenient and if the main disconnect is closer to the proposed location of the charger, then you can maybe connect into the main disconnect instead. You know, your main circuit breaker for the house might be outside, right outside the garage. And maybe you want to charge your car in your driveway. So there are rules and National Electrical Code that says you can tap right into that main disconnect. And you can tap in even ahead of the main circuit breaker if necessary. Not ahead of the meter, but ahead of the main circuit breaker, between the main circuit breaker and the meter. And you generally want to make sure that you have a disconnect, a fuse disconnect within 10 feet of that. And then you can run your charger, whether it's a 40 amp or 50 or 30, whatever, to the outlet close enough so that when you plug in your car, you're close enough to the outlet to plug in. So that's another option. You need to know the size of the charger. And once you know the number of amps that the charger uses, you multiply that by 125%, and that tells you how big the fuse has to be, or the circuit breaker. OCP means overcurrent protection. And that also tells you how big the wires have to be, whether they're going to be number 10, number 8, number 6, depending on whether you're talking about 30 amp, 40 amp, 50 amp, or 60 amp circuits. And you compare that charger ampacity with the main overcurrent protection, and you follow the rules in National Electrical Code 240.21b2. Okay, and this is a tap rule if you're going to tap on the line side of the main circuit breaker. So the rules are there, and if you're interested, you just go to your National Electrical Code, borrow one, find one online, whatever. More questions, let's take a look. Where did 96.8 amps come from in the response to that residential answer? Oh, the 96.8 amps. I keep forgetting that not everybody is an electrical engineer. If you've looked in your electrical panel, let's say you've got a 150 amp main breaker, you might notice that the sum of the numbers on the handles of the breakers in your electrical panel probably add up to more than 150 amps. And the reason they do is because over the years, it's been well established that nobody runs everything to full power at the same time. And they've got good conservative estimates of the absolute maximum amount of power you're ever going to use, depending on what you've got in that house. So the loads that were listed in that calculation were the worst case situations that would happen. And the National Electrical Code allows you to diversify and recognizes that you're never going to have everything on at once. And the worst case you might expect is what you come up with, that 100% of the first 10,000 watts or first 8,000 watts in this particular case, plus 40% of the remainder. And from hundreds and hundreds of measurements, it's confirmed that no matter, even if you turn everything on, you have a lamps plugged into 15 amp circuits, but the lamp is only drawing half an amp, and you got 5 of them doing that. So you have a 15 amp circuit fully loaded to 2.5 amps. All right, so that's where the 96.8 amps came from. It's a diversified load, and you simply divided the diversified load in volt amperes by 240 volts. Okay. So I still have 2 spaces open on my 240 volt, 200 amp panel for a 2-pole breaker. Well, Julius, it's time to go looking for an electric car this afternoon. Looks like you're good to go. You can do the calculation, of course, make sure, but I can tell you that typically we do recalculations of the actual load on a 200 amp panel, and the load typically comes out less than 150 amps. So if you throw an electric vehicle charger in there, it's still oftentimes less than 150. So are you thinking about buying electric, or do you already have one, Julius? What's the story here? All right, so what I'm trying to point out here is if you're interested in getting involved in electric vehicles and electric vehicle chargers, everything you need for your toolkit is, well, in addition to just the manufacturer's literature on what's out there, but in terms of the actual installation, it's all right there in the National Electrical Code. One thing that sometimes comes up is people say, well, if you're charging batteries in your garage, you're going to have ventilation. Well, yes and no. If you are charging lead acid batteries in your garage, they give off hydrogen, and yes, you need ventilation for that. But if you're charging lithium batteries, they are benign and they do not give off hydrogen or lithium or anything else. And so no additional ventilation is required if you are charging lithium batteries for an electric vehicle. And that's another thing that some people try to hold you to in terms of charging batteries. So the answer is right there on that one. Here's another question. Let's see what we got. Oh, that was an answer. Thank you. Must have got the right answer then. All right, let's see. I had a Toyota hybrid a couple years ago, but considering electric in the next year or so. That must be Julius, who's got that 2 pole spaces left. Yeah, well, Julius, you might use those 2 poles. I don't know if you got solar on your house yet, but those two pole spaces could be used to charge your Toyota or to add solar. But don't worry, you can do both of them. Whoever does it will figure out how to do it. Okay. And a Toyota hybrid's fine automobile. We had a Toyota 2007 Toyota hybrid, and then had a Honda hybrid, and then we finally decided to go into plug-in hybrid. Okay, let's see what's coming here. The larger main breaker reduces the distance to the branch circuit over current protection to 10 feet. In other words, line side taps that we're talking about here, you need to be careful in terms of a fault in the circuit, a short circuit. If there's a short circuit and there's nothing to protect that wire, generally, if it's less than 10 feet, it's felt that it's less likely to be damaged. But if it's more than 10 feet, if that wire is damaged and shorted, you can take down a neighborhood, or at least at 4 houses or so, if that transformer doesn't, if the main fuse on the transformer doesn't blow fast enough. Or you can have some dangerous results from arc flash or any number of different things. Here you go. This is equipment. This is a meter room for the some of the units in a condominium building. And look at that nice blank wall. Look at that gutter above. All the power to all the units that are fed by these meters go through that gutter. So why not put a disconnect here 10 feet away from the meter? And maybe that meter, since the feeders to the units go right there, that means you might be able to tap into those wires, and maybe that's your meter 10 feet away, and the garage is right on the other side of the wall, so you run a conduit out to the plug that you plug in your charger, your level 2 charger, after you've done your calculation, and off you go, charging your car at level 2 every night. Or maybe only every other night, depending on how far you drive. So, yeah, generally where there's a will, there's a way. You just need to look around for it. NEC at 625 is on EV charging stations. And here's the thing about sealed and does not release gas, okay? And fasten in place and rules and things. Again, this is stuff you can read from the slides if you've downloaded them. And they're trying to do some interesting things with wireless power transfer equipment, like you might be doing with your toothbrush now, or your hearing aids, where you charge them up by not connecting wires, but they simply use transformer coupling between the electric toothbrush and the toothbrush charger. Not as efficient, and I don't know what future is in there for wireless power transfer equipment. I think the jury is still out on that one, because you got to be pretty close. There's some interesting things to do to get a good, efficient transformer connection between the supply and the vehicle. We'll see what kind of creativity it comes out to make that from an efficiency standpoint viable. And if you want to get your product listed, then the manufacturing specs are in part 2. So 625 had a lot of good stuff in it. Again, it's all on how to do the calculations. And things like disconnects and so forth. So as I mentioned, the 625.48 already covers interactive systems. And it references 702 and 705. 705 is utility interactive systems. And UL 1741 says that if you're going to dump AC power into the grid, it has to be good AC power. It has to be nice and clean, very little pure sine waves, less than 5% total harmonic distortion, things like that. And it's supposed to be more than 18 inches above the floor, because you never know what's going to be kind of gasoline fumes or whatever might be accumulating within 18 inches of the floor. But that's a general rule for any outlet in the garage. It has to be more than 18 inches above the floor. A little more 625, but let's move into the evolution of chargers. And as you can see, we are evolving into the bidirectional world. And I think within 5 years, we'll have made that transition. We'll see. I could be off by a few years here. You can hold me to that prediction if you want. I don't know what I'm going to have to. Well, I guess if I'm right, you can say I was right. And I guess if I was wrong, you can say I was wrong. Yeah, all right. I've been wrong before. Energy efficiency, another totally different topic. Let's take a look at it, what's out there. Read an article about Amory Levins not too long ago. Amory runs the, well, I guess he's now maybe sort of retired. He's the senior official in the Rocky Mountain Institute out in Snowmass, Colorado. And he's been doing energy efficiency since the mid-1970s. And he is one sharp cookie. He wrote a book about hard paths or soft paths. And I have to actually say that Amory, in writing that book, is the guy who got me started back then. I had the pleasure of meeting him one time, and he's an incredibly bright guy. So anyway, and he pushes solar, but he also pushes energy efficiency. And the reason is because there's millions of inefficient buildings out there, and they all can be made better. If they heat space, food, water with fossil fuels, usually they can be replaced with renewable electric equipment. Okay, because now our friend who just put in a new heat pump, when he puts in solar, that solar is going to be powering his heat pump, and he's going to get free heat. And if he puts in lots of insulation and stuff, then he'll get some passive solar heating through his windows as well. And that electricity can be used for things other than heat. So lots of things there to look at. Refrigeration is a whole lot more efficient now. Air conditioning, ventilation, they can all be made more efficient. Lighting, my goodness, LED lights, 10 times more efficient than incandescent lights. Better doors and windows. You get a lot of benefits from better doors and windows generally. Less infiltration, less heat transfer, less sound transfer. and hurricane proof, all rolled into one check for $15,000 or something like that. All depends how many windows and doors you got. That's about what it costs us to redo all our windows and doors. You can plug up air leaks. There's ways to find them, and there's ways to get them plugged up with various kinds of insulation. You can upgrade your insulation to a point where the additional heat loss would take the electricity it saves. It would take a long time to pay for the additional insulation. So R38 in the far north, but R19 down south is generally good enough because the difference in temperature between the attic and the inside of the house is not all more than generally 30 degrees maximum for cooling or heating. More energy efficient, water efficient landscaping. You don't do any of these unless they pay back. Now it's weird because we do a lot of stuff that doesn't pay back. You know, that fountain, that statue, that whatever. What's the payback on them? You know, after a certain number of years, do we get our money back? No, we don't. Sometimes we just do things because we want to. But sometimes we do things because it's smart to do it, because it saves a lot of money and it saves energy and it saves the planet and all that. Oops, here I go again. What about air conditioning systems? Here's an interesting system. This is your, I don't know if your heat pump is an inverter technology mini split or not, but here's a mini split that has an SEER of 33.1, and it works down to -13 Fahrenheit. And you sit there and have your breakfast and control it with the remote control. You don't even have to walk to the thermostat. You just have to remember where you left the remote control. There's energy recovery, ventilation. You plug up your leaks and use one of these to get fresh air in. But this is a countercurrent heat exchanger so that when the cold air comes in, it's warmed by the warm air that's going out. And they're about 90% efficient. So why let all your infiltration be just cold air coming in without being warmed first by the warm air that goes out? Saves 90%. I mean, that's a lot. If you have a humidity issue, you can do, if you do energy recovery, if humidity is important, because this has to have a condensate drain, the top one, on the energy recovery unit, because not only does it take the humidity out of the incoming warm air, but it takes the heat out of that. I'm sorry, not only, I'm talking too long, I guess. Not only does it remove the heat and transfer that to the cool air going out, but it removes the humidity from the incoming air and it runs it down a condensate drain. If you're up where the humidity is not a big issue, you can get by with a plain old heat recovery ventilation. And again, it's countercurrent heat exchanger. As you can see, you've got outside air, outside air in, outside air out, inside air in, inside air out. They run past each other in there, transfer the heat. And heat always transfers from hot to cold, whichever way, but it doesn't make any difference because the direction of the air is going in the direction where you benefit from it. So HVAC systems, they're amazing things. Here's a question. Let's take a look. Yes, it's a mini split, 22. Okay. That's a nice number, isn't it? SEER 22. And what that means, that's your ratio of, let's see, SEER is BTUs per watt. So it's a mixed unit, and it works on, but we can convert SEER to coefficient of performance, which is watts divided by watts. And basically what you're looking at with an SEER of 22 is something like a 4-to-1 advantage. You're taking, your heating is one unit of electricity to 3 units of outside air, to 3 units of environmental heat. Of course, when you're heating with the mini split, you're making it colder outside because you're taking the cold from your house and you're dumping it outside. But I haven't heard any complaints about that yet, any more than taking the heat from your house and dumping it outside with your air conditioner. Let's see. Okay, yeah, thanks for you. One of the first people I know who did that. I wanted to get, well, we're moving on to water heating systems here. And this is also a major transition happening here. You compare the lifetime of electric water heating versus solar water heating. And solar water heating is a little more complicated up north. You got to watch out for freeze, watch out so it doesn't freeze or it bursts the pipes. Florida doesn't have quite that same problem. But 40 years ago, when photovoltaic electricity was very expensive, the only way to make hot water was to get solar domestic hot water, a solar water heater. But now it's a toss-up because it's very interesting. The heat pump water heater, first of all, produces about 3.5 kilowatt hours of heating for every kilowatt hour of electricity. Okay. And if you do that, that means you're taking a lot of heat out of the air and or cool out of the water and dumping that into the space around the heat pump water heater. So if that's in your garage, every time that thing turns on, it cools down your garage a little bit. And that could be a nice thing in Florida. I really seriously was considering one of these, but in our condominium here, we have kind of a tight spot where our water heater is located, and it's a lot of humidity in this area. And I was really concerned that if that cold air came in contact with certain surfaces, we would get condensation, and condensation leads to mildew. So it's something you need to be a little careful. Of course, a lot of people don't want to air condition their garage in the winter either. But generally, the amount of air conditioning you get is relatively inconsequential compared to otherwise, but you get some, depending on how much water you use. But you look at the dollars on this, and either utility or photovoltaic powered heat pump water heaters just may be the most cost-effective way of making domestic hot water now. Because consider if you've got solar electric making your hot water, when you're not making hot water, that solar electric is doing other things for you or being sold back to the utility. When you're making solar domestic hot water, if you're a part-time resident, say 50% of the year, then only half of the year that solar water heater is working good, doing good things for you, but your neighbors can't use that solar hot water. So that just sits there not earning any money for you for half a year. If you're a full-time resident, that's another story. I'm just saying that it's worth doing the analysis now and do the numbers and do those things that lead to the most efficiency. And here's its picture of a 50-gallon water heating heat pump. The compression heating is on top. A water heating heat pump is just like an air conditioner, except it a reverse cycle air conditioner that heats air, but instead it heats water, and it takes the cold out of the water and dumps it into the room. Okay, what else we got? Smart irrigation controls are out there. We were staying at a friend's while our place was being remodeled. And when it rained, we'd call her and say, it's raining. And she would override her irrigation device with her cell phone. Tell it not to turn on that day. So it's interesting. It's not only that, some of the smart irrigation now can actually adapt to the kind of grass you've got and how much water it needs, the kind of soil you have and how much water it soaks in, whether or not the grass is in the shade versus in the sunshine, and whether it's hot or cold outside. All of those things affect the amount of water that your lawn needs. The smart irrigator, that's why they have sensors. They sense all this stuff and they water it accordingly. And there's a popular system likes to communicate via Wi-Fi. So you want to make sure that your communication protocol is compatible with however you want to communicate. Of course, if you're pumping that water, and whether, even if you're buying water, that water is still being pumped by somebody. So saving water saves electricity as well. And not only that, it's probably using some electricity in the purification process and so on and so forth. So you really can't separate water conservation from energy conservation, because when you use less water, ultimately you're using less energy. Zero energy buildings we mentioned earlier. Let's do some math on them. Here's the definition. You've got a site boundary. It could be just your yard, but it could be your neighborhood or a school campus or something like that. But it's within that site boundary. Now, also within that site boundary, you have a renewable energy production site, whether it's wind or solar or both. No reason why it can't be both. And they produce at least as much energy as needed by that building. And it's not hard to show that that happens. I can tell you that in the last 24 hours, I've reviewed maybe 15 to 20 sets of plans for solar systems for homes, residential. And the average size is around 10,000 watts. And that is enough for most buildings, most typical 1,800 square foot house, to make a year's worth of electricity. We'll take a look here. But anyway, right now we're going to talk about zero energy buildings. All right. And so at night or when the wind isn't blowing, you need to supplement some way or another, either with battery storage or by buying it from outside. And it's possible that some of the delivered energy you get from outside is made by solar or wind. So when you're not using it within that building campus or whatever, then you're selling it back to wherever you bought it. And the definition of zero energy is that the exported renewable energy is equal to the delivered energy. And if that's the case, then it's a zero energy building. Now, there's a trick to that, because there's the energy that it takes to make a kilowatt hour of electricity is more than a kilowatt hour if you're burning coal, for example. So we need to look at some conversion factors here. So let's take an example here. When these people move back in, they're probably going to want to pay attention to what we're talking about here. We have to talk about direct energy usage. If you're burning coal to make electricity, you can't convert 100% to electricity. So here's the conversion factors. A direct conversion, a kilowatt hour, is equal to 3,413 BTUs, okay? And as you all know, 1 BTU raises the temperature of 1 pound of water by 1 degree Fahrenheit, just to get a rough idea of what a BTU will do. A therm is 100,000 BTUs. In case you didn't know that, a barrel of oil constitutes 42 gallons, and within those 42 gallons, there are 5,800,000 BTUs. And a gallon of fuel oil number 1 has 137,400 BTUs. And that's for use that if, in fact, you're burning fuel oil number 1 in your house, and if you know how many gallons a year you're going to burn, you know how many BTUs you get from it. Okay, so first thing you do is you make a list of all your energy sources and the estimated use, and then you convert everything to source energy equivalents. Let's do that just to see how simple it is. When these people rebuild, they might want to consider it as well. Love it. Those California fires are incredible. let's assume a dwelling annually uses 7,500 kilowatt hours of electricity and 500 therms of purchased natural gas. Reasonable numbers, and of course you can take any specific building and use the exact numbers for those buildings and carry the same analysis on with different numbers. So if we convert the electricity to BTUs, we got 7,500 kilowatt hours times 3,413 BTUs per kilowatt hours gives us 25,597,500 BTUs. That's a direct conversion if we could make electricity 100% efficiently, but we can't do that. So therefore, the electricity to make that electricity is going to take 3.15 times that, or a total of 80,632,125 BTUs. So if you burn 80 million BTUs worth of coal, you can get 25, almost 26 million BTUs of electricity. Okay, and these are the agreed upon numbers within the industry. Some is made more efficiently, some is made less efficient. We'll see. Overall, they've agreed on 3.15 as a reasonable number, and it has nothing to do with pi as 3.14 or anything like that. Natural gas into source energy, the 500 therms of natural gas, you need to multiply by 1.09. Now, why multiplying only by 1.09 for natural gas? Well, if you have a natural gas heater, you're just burning it to make heat. That's mostly what you're doing. And most heaters now are about 90% efficiency, so you don't lose much, maybe 9%, as indicated here by this formula, okay, or whether it's industrial or whatever. And so if we add the two energy sources, the source energy associated with them, we get 135 million BTUs of source energy in a year's time. Okay, so now what do we have to do? This means we have to replace that with that renewable source, 135, 132, 125, okay? So we have to offset it. And if we do it with photovoltaics, then we have to estimate the number of kilowatt hours per kilowatt per year for the building, and then determine the size of the system. Well, it turns out that's easy. For one thing, the National Renewable Energy Labs has a great program called SAM, System Advisory Model, that you can download for free. It's paid for with taxpayer dollars, and you can estimate. But if you do this estimate for a nice south-facing array, and not everybody has south-facing arrays, that's why NREL SAM is useful, because it can tell you what a west-facing array will do for you, depending on what the roof tilt angle is and where you live and so forth. But just doing a rough estimate, 1,500 kilowatt hours per kilowatt per year, and converting to BTUs, this means that for every kilowatt of photovoltaics, you can generate 5,119,500 BTUs per year, just like the very first step we took in the beginning. And, we're going through these formulas to show you that, yeah, this is some of the meat of the system. And if you really want to use them over, download the slides, because also the slides have the answers to everything in the quiz. So you might as well download the slides so you can dig back and find how you get the answers to the quiz questions, okay? Without them, it means you have to memorize all this stuff I'm just telling you, and some of you might, but I didn't. I had to read it. Anyway, we got to compare apples to apples. So we have to compare this electricity to the electricity that is being bought from the utility. So we get to multiply these solar BTUs by 3.15, and it gets us up to 16 million. Okay. And that's what we're going to need. That's what we get for each kilowatt installed. Okay. In terms of source energy. So now, how much source energy do we need? Divide that by the amount we can get from a kilowatt. So we got our 135 million divided by 16 million, and it means we need an 8.38 kilowatt system. The average system we're designing these days is 11 kilowatts. So And we are talking about houses with electric bills that are much lower than 1,500 kilowatt hours a month or whatever, or 1,500, 7,500 a year. So this is something that is very much doable. Okay. And let's look at some numbers. 20% is the typical efficiency of a solar array now, converting 20% of the sunlight into electricity. And if you can do that, for every square meter of sunlight shining down on your array, you can make 200 watts under standard test conditions, okay? So what we're trying to do is size the array. How many solar panels does it take to make 8.38 thousand watts, and how much area is that going to take up on your roof? Well, 8380 divided by 200 is 41.9 square meters, which happens to be 451.712, no, 0.127633. We rounded that off. Square feet of south-facing roof space. 451 square feet. Well, gee whiz, 3 times 15 is 45. So if you got a 15-foot by 30-foot roof, and if you're using 300-watt modules, and nobody uses them anymore, everybody uses 400 watts or 440 watts are the most popular ones going these days. But for 300-watt modules, you need 28 of them to fit into those 451 square feet. Okay. And you're going to pay about $2.50 a watt for this system. If that's part of your mortgage, or it's guaranteed for 25 years. So if you just price it out over 25 years, your monthly payment on that is that's where that LCOE came from at the beginning of the story here this morning. So you just need to make sure the modules will fit. Typically, modules are measuring in the neighborhood of 1 meter by 2 meters, some 1 meter by 1.5 meters. So there are trade-offs, and there's a question. Let's take a look here. With these calcs, recommend using microinverter modules. I can tell you that for residential systems that we are currently designing, roughly 90% are with microinverters. The reason for microinverters is that every module has its own inverter. Therefore, if one module is shaded, it does not affect any of the other modules in the system. We use several different kinds of microinverters. The other option for residential is another reasonably good option is optimizers. So microinverters mean you're converting to AC immediately at the module. And AC at 240 volts is being delivered from the roof to the ground. An optimizer system uses a DC and a single inverter at ground level, and it converts the DC and optimizes again on an individual module basis on the roof, and it brings down the power at 400 volts DC instead of 240 volts AC. So right now, I can just tell you that the microinverter modules are more popular, at least in my area, by about a 90-10 ratio. Okay, building plus appliances can be made more efficient, then you can use a smaller photovoltaic array. Obviously, trade-offs here. What other trade-offs? Well, you just compare your costs of more efficiency. And this is where you're, for example, adding more attic insulation. Should you add more attic insulation, or would that same amount of money put into a PV system give you enough electricity to charge your electric vehicle? Because it typically takes between 1 kilowatt and 1.5 and 2 kilowatts of photovoltaics on the roof will charge your electric vehicle. Now, of course, if the vehicle isn't there, what you'd argue is that it makes enough electricity to charge your electric vehicle, or to offset the cost of the electricity that charges your electric vehicle. Or if you store it in batteries while you're away, you can empty your batteries into your electric vehicle at night. That's not terribly efficient or cost effective right now, not necessarily the best way to use batteries. When you orient your PV in different directions, they decrease the performance, and a lot of people wonder how much. So we want to take a look at that. And if you're not looking south and you're making your 1,500 kilowatt hours per kilowatt per year, then you just add more kilowatts to the roof in order to still make the more kilowatt hours. Okay. Here's your savings and energy costs versus additional mortgage payment for 6 US cities if you build a zero energy building. And look at these differences. Sure, you're going to spend more. Atlanta, 19,000 more. Baltimore, 15,000 more. Chicago, 19,000 more. Okay. But look at the difference in monthly energy savings versus the additional mortgage costs. $52 in Atlanta and well over 100, let's see, 117 and $126 savings per month for a zero energy building in San Francisco. Why is that? Well, electricity is a little more expensive in San Francisco than it is in Atlanta. So you're looking at the cost of electricity. So it's almost silly to even think about building anything other than a zero energy dwelling at this point. Talk a little bit about energy storage here. Okay, we've had a few questions about it. Let me look at my clock here. Oh, we got to go quickly. We're going to talk fast, but again, all the answers to the quiz questions are in it on the slides. You may have to do a little calculation, but the calculations are multiplication, division, addition, subtraction. We've talked about, well, small energy has been around a long time because that's the kind of PV systems we used to have up until the year 2000. They were a little cabin in the woods that stood alone by itself. But there's also DC coupled grid connected systems and AC coupled grid connected systems, and that use energy storage. Okay. In the past, they've been kind of expensive, but you have to consider energy storage as an insurance policy as opposed to an investment in actual return on investment in dollars. You have to decide what's it worth to have a house that has a refrigerator that works after a storm, lights that work, and so forth. So these have been costly and complicated. And somebody asked a question, made a comment about New York and energy storage. The old-fashioned ones had to be programmed on site and so forth. And so usually what people ended up with was just a straight electric system. But then along came Mr. Musk, so you can do this. Sure, you're still connected to the utility. And you have still a main disconnect with feed through lugs on it, and maybe some loads in there that are interruptible. And then you connect this here automatic relay. And then you connect this here main distribution panel that has a main circuit breaker in it. And here we have uninterruptible loads. At least we're going to make it that way. If we add a few more things. If we add a panel here that combines some stuff, then we have to have some stuff to combine, and maybe a solar system here that makes some AC electricity. This could, in fact, be a microinverter powered system. And we're dumping AC into this utility graded AC into this combiner panel. And at this point, this is all good when the utility is up, but now the utility goes down, we add this little thing here, the power wall. And when the utility goes down, that automatic relay contacts opens up, you disconnect from the utility, and the power wall now plus the solar array now provide power to your uninterruptible loads. And if you got enough power walls there, had a house that installed 8 power walls a while back at 13.5 kilowatt hours each. That's a lot of backup storage. They backed up the entire house. So forget about interruptible loads. They didn't have any. Okay, so we got to hurry. And here's some words that describes what's going on. Okay, and basically, the systems are a whole lot more straightforward now than they used to be. No user programming, well, a little bit with the automatic relay stuff and some of the monitoring system. So you can size the PV and storage. I'm just going to, we've used up our time, had a little more discussion than usual today. But if you want to size the PV and storage properly, again, if you want to do it, the information here is for you to know that, yeah, it's very straightforward process to do it. Okay, so here it'd be nice to have 20 kilowatt hours a day of storage based on utilization and what you'd like to be able to power and so forth. And 20 kilowatt hours of storage is pretty common. Two N-phase 10 kilowatt hour batteries will do the job for you. There's large energy storage systems out there as well. Here's pumped hydro. This is a 1 megawatt rotating flywheel mechanical energy storage. Batteries. These are lithium batteries. More batteries. You can see by the walkway around this, the liquid in these batteries. And if it leaks, you don't want to walk through the liquid. But these are on the horizon here and in use. The batteries right there, those lithium batteries, they're selling a lot of those. Here's a big battery in Australia, 100 megawatts in 100 days. That was what Musk was challenged with, and he did it in less than 90 days, or in 100 days. And in 140 milliseconds, this whole battery system can switch over and be fully up on the grid. So at 129 megawatt hour storage capacity, that's a whole lot more than my 17 kilowatt hour storage. So yeah, there is big battery stuff out there and it is working. If you want to read about it, here's the references for you. This one online at the end of 2017. Okay, I'm going to click through here quickly. Again, we've had our fun with the earlier stuff, but I just wanted to make sure that everybody is aware and has a chance to take a look at this later. Even microgrids, you can have a substation in a whole neighborhood that has all of these things. So what happens to the grid? Here's what we've got mostly now. You generate it, transmission to substations, large users, small users, medium users. But in the future, it's going to be bidirectional. The only place you got to be careful is at the generation, because generators, the fossil generators, any rotating generator, if that electricity tries going the other direction, it's going to try to turn that generator into a motor, and the prime mover is not going to be happy. So that bidirectional link is very important to make sure that none of this other electricity finds its way into a fossil backup generating system. So that's the beginning of the story. A lot of times you'd say that's the end, but we are at the beginning of an era of some exciting stuff, folks. And I hope you'll all be able to be a part of it, because I think you'll find it very rewarding. And that's the end of it today. Unless anybody has any more comments or questions, I'm going to look at Q's and A's for just a short time here. Here's one Q&A. Let me just click on that so it comes down. Oh, hey, questions. That's what I'm all about. I'm more than happy, and thank you for asking them, Walter. Okay, I see no more questions on the chat. We've run a little, or I mean, on the Q&A. Read through the chat, tells you where to find the quiz. Be sure to download the slides because that's where the answers are. And the quiz questions go in the order of the slides. So I can tell you that much. And from there on, you're going to have to figure out the answers. And I understand how nice it is sometimes the answers ahead of time like that, oftentimes on the courses that are not live. You can download the questions and then you just answer them as you go through. A little extra work here. Sort of means you go through the material again, but maybe you learn a little more as well. I hope your morning has been well spent, ladies and gentlemen, and I hope that you all have a great week for the rest of the week. I'm going to stop sharing my screen now, and thank you all for being here. And those who are chatting, all those answers will come to you from the host. I'm not sure about those answers, but you'll get answers from the host.